after we discussed the basic concepts related to multiple regression models, now let's look at how to do F-test so that you can make joint hypothesis testing for multiple regression models. So first of all, let's just look at how an F-test works. So for this part, you really basically need to know how to perform this test mathematically. So F-test is based on a comparison of sum of square errors from the unrestricted model to the sum of square errors from restricted model with J restrictions, in which the null hypothesis is assumed to be true. Well, this sounds a little bit abstract, but you are going to see that they have very, very concrete meaning in a very short moment. So this will be how a F statistic look like. So basically, it is like the sum of square residual of the restricted model minus the sum of square residual or sum of square error of the unrestricted model divided by J. That's in the numerator, and the whole thing divided by the sum of square residual of the unrestricted model divided by n minus k. N minus k will be the degree of freedom of your estimation. Okay, so let's look at the intuition of F-test or F-statistics. So in general, this is how it works. When you add more restrictions into model, in general, you should have worse fitness of the model. So the fitness of the model should go down. And when the fitness of the model goes down, then you should generally have a larger sum of square residual, because sum of square residual is something like an inverse measure of how good or how fit a model is. And not surprisingly, we should also understand that when you have more restrictions in your model, then it means you have fewer coefficients, because restrictions are usually in the form of whether a coefficient is equal to 0. And if you assume that a coefficient is 0, then it means that this coefficient is just more or less removed from your model. Okay, so when you do this joint hypothesis testing, when the newly added restrictions are reasonable, then what you should see is that even the sum of square residual should go up. It shouldn't go up by too much. Okay, so in this case, you should also not see a very large change of F statistic, or you should not change a very big F statistic. Or otherwise, if the restrictions are very harmful for the fitness of the model, it makes the model very inaccurate, and it makes the sum of square residual go up by a lot, then in general, you should see a very big F statistics, and that's also an indication that the restrictions are not so good. So just kind of let's just go back to the definition of F statistics. So in the numerator, the F statistics includes the term of the difference of sum of square residual of the restricted model and unrestricted model. Okay, so when you add more restrictions, in general, this term, the first term, should be larger than the second term. Okay, if the restrictions are very reasonable, so even though this is larger than this, the difference shouldn't be very big. But when you had many restrictions, or the restrictions are not so good, then this one should be much larger than this one, and that should give you a very big F statistics, which is also an indication that the restrictions are not so reasonable. Okay, all right, so let's just look at an example. So suppose that we just use the housing price equation again. Okay, so we estimate an equation where the log of housing price is equal to beta 1 plus beta 2 times square foot of the house plus beta 3 times the number of bedrooms. Okay, the number of bedrooms plus the area term. And we want to do a joint hypothesis testing of beta 2 is equal to beta 3 is equal to 0. Okay, so remember in lecture 3, when we have hypothesis testing, it's a single one. So it's either beta 2 is equal to 0 or beta 3 is equal to 0, but not both. But when you do a joint hypothesis test, it means that you have multiple equations or multiple restrictions on your model. Okay, so first thing first, let's be clear about, so if this is a null hypothesis, this is a null hypothesis, beta 2 is equal to beta 3 is equal to 0. What is the alternative hypothesis? Okay, so here you need to be very clear that the alternative hypothesis of beta 2 equals beta 3 is equal to 0 is not both beta 2 and beta 3 are not equal to 0. Okay, so the alternative of both beta 2 and beta 3 are 0 is not both beta 2 and beta 3 are not 0. Okay, it should be at least one of beta 2 and beta 3 is not equal to 0. Okay, so basically when you have null hypothesis, the alternative hypothesis refers to the case where the null is not true. Okay, in order for both beta 2 and beta 3 are 0 to be untrue, you don't need both of them to be different from 0, but as long as one of them is different from 0. Okay, so the alternative of beta 2 is equal to beta 3 is equal to 0 is as long as one of beta 2 and beta 3 is not 0. Okay, and in this case, what is the restricted and unrestricted model? Okay, so in this case, we should know that the bigger model with more coefficient, or so to say, the original model is the unrestricted model. Okay, the unrestricted model. And what is the restricted model? Restricted model refers to a case that when the restriction or the hypothesis is true. Okay, so when beta 2 and beta 3 are in this 0, you should have here is a 0, here is a 0. So actually the restricted model is very simple. Restricted model only has one parameter, that is the constant term. So as we know before, restricted model is actually smaller or has fewer coefficients compared to the unrestricted model. Okay, so the restricted model in this case is very simple. It's simply log of housing price is equal to the constant term. All right, and how do we do the test? So first, let's try to find the sum of square residual or sum of square errors for the unrestricted model. So we regress the housing price on a constant, on the square foot, on the number of bedrooms, and the sum of square residual or sum of square errors can be found here. So it's like 111 something. Okay, and then we estimate the equation, the restricted model, where the log of housing price is regressed on beta 1, the constant term only, right? This is the restricted model. And here we see that the sum of square residual becomes 296 something. And of course, this is bigger than the previous one, okay? When you have more restrictions on the model, the fitness of the model tend to decline, and the sum of square residual of the model tend to increase. Okay, then it's just a matter of whether the increase is very big or not. Or if that's very big, it means that the restrictions are not reasonable, which is probably bad. And if the increase of sum of square residual is not so big, it's probably an indication that the restrictions are okay. All right. So if we want to calculate the F statistics, we already know that this is the sum of square residual of the unrestricted model. This is the sum of square residual of the restricted model. Number of restrictions, okay, beta 2 is equal to 0, beta 3 equal to 0, 2 restrictions. N minus K is, we know the sample size is 10180, okay. You have 3 parameters in the unrestricted model, so K will be equal to 3. So the degree of freedom, the bigger degree of freedom, should be N minus K equal to 1077. And if we plug in all those values into the equation, you will see that the F statistics is equal to 800 something, which is a quite big value. Okay, and the next is just to compare this F statistics to the critical F statistics. okay? And in this case, it's a one-sided f-test. We just need to look for the 95 percentile of f distribution, okay, with 2 degrees of freedoms. With the first one will be 2, the second one will be 1077. So this will be the critical f to compare with. And since 896 is surely much larger than 3, so f is larger than critical f, then we should reject null that both beta 2 and beta 3 are 0. So this is how an f-test works. Okay, and if you want to do that in eViews, if you want to do that in eViews, actually it's not so hard. It's not so hard. So if you run the regression, when you see the regression output, you can simply go for View, Coefficient Test, and then you find so-called wall test. Okay, so there is a different name, a special name of this test for joint hypothesis on coefficients. So this special kind of f-test is also called wall test. Okay, if you go for wall coefficient restriction test, if you just key in C2 is equal to C3 is equal to 0, because eViews call the coefficient C instead of beta or B, then eViews will tend to give you the output directly. Okay, eViews will tend to give you the output directly. Okay, and after that, let's just look at one special case of the f-test we just discussed. Okay, so there is something called test the specification of a whole model. Okay, so what does it mean? It just means that when you have a multiple regression model, okay, so one thing you want to know is that whether all the coefficients as a whole make sense in terms of explaining the movement of y. So in this case, we say that if you want to test the specification of the model or test the significance of the whole model, then you want to test the null hypothesis is whether all the coefficients are 0, where the alternative will be that whether at least one of your coefficient is not 0. Okay, so this is a test for you to see whether at least of your x makes sense, or at least your model makes a little bit sense. And in this special case, you should also see that the sum of square residual of the restricted model should be again just regressing your y on the constant, and sum of square residual of the unrestricted model should be the whole regression, and the degree of freedom should be k minus 1 restrictions, given you have k coefficients in total. And in this case, you can also see that so there's something called f statistic when you do the eViews regression. Okay, so maybe the circle is a little bit too high up, but basically when you run the regression at the beginning, when you see there's something called f statistic of the model, you may feel puzzled. What does it mean? But here you can also see that this f statistic is just the f statistic of this test. Okay, so basically we see that f statistics of this model is 896 something, and the p-value is about 0. So basically when you see this, you should also know that basically it tells you that the model as a whole is still kind of significantly different from 0. So at least one of the coefficient is different from 0. Okay, and also remember that for this special model, it's just what we did just now for here. So we can also see that the f statistic in this output is exactly the same as the f statistic we calculated by hand. It's a suggestion that we did the right thing here. Okay. All right, and finally, just a side remark about like the relationship between t-test and f-test. Okay, so basically, for individual two-tailed tests, you should know that both tests are actually equivalent, and for the simple regression model, there is a numerical relationship between the two, where it's simply the case that the F statistics of a one variable univariate regression or simple regression is equal to the square of the T statistics. And for multiple regressions that we study in this chapter, when you have more than one coefficient, usually we will refer to F-test more often than T-test. So basically, you should know that F-test is just something like the multiple regression version of T-test.